Welcome back to the deep dive. We're here to sift through those piles of sources and really pull out the core insights, helping you get genuinely informed. Today, we are tackling something, well, it sounds almost mythical, doesn't it? The ether. But it was, for a long time, central to physics. And our specific mission today, the question we really want to nail down is this. Is the ether, the one Einstein envisioned, actually capable of having momentum? Can it carry motion? And related to that, does it have inertia? Can you push it? Does it resist being moved? So to dig into this, we've looked at an excerpt from Einstein's really important 1920 lecture, Ether and Relativity. And we've also pulled from a discussion on a key principle called Lorentz Invariance. Get ready, because this might just stretch your understanding of space, time, maybe even reality itself. Okay, let's dive in. Before Einstein shook things up, this idea of an ether, it wasn't just some fringe theory, was it? It was pretty fundamental, especially for light. What exactly was this luminiferous ether they talked about?
Yeah, absolutely. In the 19th century, you had major figures like Maxwell, Lorentz. They really built this picture. They pictured the ether as this continuous substance, maybe,
Yeah.
a medium that filled absolutely all of space, everywhere.
Like a universal background.
Exactly.
Yeah.
Think of it like an invisible ocean. And light waves were ripples traveling through that ocean. See, for light to be a wave, they figured it needed something to wave.
Right, makes sense. Like sound needs air or water.
Precisely. So this ether, it had to be kind of flexible, deformable, so waves could pass through it, but also, and this is tricky, incredibly rigid to support transverse waves, which light waves are. And crucially, they believed it was separate from normal stuff with weight. And they thought it defined an absolute frame of reference, a sort of universal still point. It had a definite velocity or lack thereof.
Okay, so this invisible sort of paradoxical substance, it carries light, defines absolute rest. But didn't this run into some, pretty big problems when people tried to actually, find it, detect it?
Oh, absolutely. That's where the cracks really started to show. There were experiments. The most famous one is probably the Michelson-Morley experiment, late 1880s. They were specifically designed to measure the Earth's motion through this supposedly stationary ether. As the Earth orbits the sun, it should be moving through it, right?
Yeah, you'd expect to detect some kind of ether wind.
Exactly. But they found nothing. Zero detectable motion relative to the ether. And that was a huge puzzle, a major crisis, really, for physics at the time. It just didn't fit the model.
Okay.
And that's precisely where Einstein steps in. His general theory of relativity didn't just tweak the idea of ether, it completely reframed it, moving way beyond that old mechanical picture.
Right, and this is where it gets really fascinating for our question today, because Einstein famously said something like, empty space without ether is inconceivable. But the ether he was talking about sounds totally different. So if it's not that old physical fluid, what is it? And coming back to our core question, does this Einsteinian ether have momentum? Does it have inertia?
That's the absolute key distinction. Einstein was very clear. The ether of general relativity is not ponderable. Meaning it doesn't have mass, doesn't have weight. You can't put it on a scale.
Yeah.
And you absolutely cannot think of it as being made of little parts or particles that you could, track over time. Follow their path.
I see.
So the very idea of motion in the way we normally think about it, it just doesn't apply to this ether. Which leads directly to the answer to your question. It has no motion, and therefore it has no inertia, fundamentally.
Okay, no motion, no inertia. So it's not a substance you can push against. It doesn't resist being accelerated because you can't even talk about accelerating it. That's a massive conceptual leap. So if it's not those things, what is it? What properties does it have? What does it do?
It's probably better to think of it less as a thing and more as embodying the physical qualities of space itself. Or space-time, really.
Qualities of space, like what?
Well, it determines the geometry, the metrical structure, how we measure distances, how time intervals elapse. It's what gives space its structure. And importantly, it's the carrier, the bearer of electromagnetic fields, and crucially, in general relativity, the gravitational field.
So when we say gravity warps space-time, we're talking about warping these properties, this ether.
Exactly. You're warping the geometrical and physical qualities of space-time. It's the framework. Einstein basically took the old idea of the Lorentzian ether and stripped away the mechanical parts, the substance, the absolute rest frame, the motion. He relativized it, making it a property of space-time, not a thing in space-time.
Okay, that's a much clearer picture. It's like space isn't just emptiness, it has inherent characteristics. So then why is it so vital? Why is it such a big deal that this Einsteinian ether has no motion and no inertia? What does that unlock for physics?
Well, that connects directly to one of the absolute cornerstones of modern physics.
Yeah.
The principle of Lorentz Invariant.
Lorentz Invariance, right. Remind us what that is.
Sure. Basically, it states that the fundamental laws of physics, how gravity works, how electromagnetism works, are exactly the same for all observers who are moving at a constant velocity relative to each other. It doesn't matter if you're standing still or zooming past in a spaceship at a steady speed. The rules of the game, the physical laws, look identical.
Okay, so no special viewpoint, no preferred frame of reference in the universe.
Precisely. There's no absolute rest frame against which all motion should be measured, according to this principle. Physics is democratic, you could say.
Right. So how does the old ether, the one with substance and potentially its own state of motion, clash with that democratic principle?
Well, if the ether did have momentum or inertia, if it could be assigned a state of motion, then it would define a preferred reference frame. You could, in theory, measure your speed relative to this ether ocean. That would be the absolute rest frame.
Ah, I see. It singles out one state of motion as special.
Exactly. And that directly contradicts Lorentz invariance, which says no such frame should exist for the fundamental laws. The old ether concept basically implied that the equations describing, say, light only took their simplest true form in that one ether rest frame. That's a big problem relativistically.
Okay.
Einstein's ether, precisely because it lacks these mechanical properties, no inherent motion, no inertia, it completely avoids establishing any preferred frame.
Yeah.
It makes the concept fully consistent with the principles of both special and general relativity. It respects that symmetry, that invariance.
That makes perfect sense. It cleans things up beautifully, really.
Yeah.
So bringing this back to the listener, why does this deep dive into ether, momentum, inertia? Why does it matter to us now beyond the physics lab? What's the takeaway?
Well, I think it shows a really profound shift in how we understand the universe itself. It's a great example of how science progresses. We moved away from a very mechanical, sort of intuitive picture space as just an empty box, or maybe filled with some invisible jello.
Right, the tangible medium idea.
Yeah. And we moved towards something much more abstract, perhaps less intuitive, but, well, more physically accurate. Space-time as an active, dynamic entity with properties.
The big takeaway for you, I think, is that space isn't passive. It does things. It has structure. It carries fields. It can be warped. And it isn't a thing in the old sense that you can push or that has momentum. It really highlights how science often involves redefining our most fundamental concepts, chucking out ideas that lead to contradictions, and embracing these new frameworks that ultimately describe reality better. It's about refining our understanding.
What a journey, really, from this almost physical substance carrying light to Einstein's redefinition, where the ether is the physical qualities of space-time itself, but without that baggage of momentum or inertia. It's not stuff. Exactly. And what's so fascinating is how this concept, the ether, didn't just disappear. It transformed. It evolved from being seen as this, tangible medium into something reflecting the deep geometric and physical properties of space-time. It really shows how our picture of reality gets richer, more subtle as physics advances. We have to let go of those simple mechanical analogies sometimes.
Absolutely. And maybe here's a final thought for you, the listener, to mull over. If this ether, these properties of space, has no momentum, no inertia, and isn't a substance, does that change how we think about the universe expanding? Is it expanding into some pre-existing void? Or is it more like space itself, with all its inherent properties, is dynamically generating more of itself, more space-time? Something to think about. Keep exploring those deep questions. We'll see you next time on The Deep Dive.